All right, so here we go. The last day of notes from Chapter 8. Again, talking about Taylor and Maclaurin series and looking at some of the power that they have in evaluating and using some algebraic manipulations. So we want to evaluate the integral e to the opposite of x squared, but do it from its infinite series. And then we want to evaluate that same integral, but from values 0 to 1, and we want to be within 0.001 of the actual value. So we know that e to the x is the series n goes from 0 to infinity of x to the n over n factorial. Here we have e to the opposite of x squared. So we replace the x with the opposite of x squared. And we can use our power of exponents, the properties of exponents, and rewrite this as negative 1 to the n times x to the 2n over n factorial. The terms for that series, when n is 0, we would get 1. Plugging in a 0, we get negative 1 to the 0, which is 1. X to the 2 times 0, which is x to the 0, which is 1, over 0 factorial, which is 1. Plugging in 1 for n, now we're going to get negative 1, because negative 1 to the first is negative 1. X squared over 1 factorial. Plugging in 2, again, negative 1 squared is positive 1. X to the 4th over 2 factorial. Plugging in 3, we get negative x to the 6th over 3 factorial, and that pattern continues. If we want to integrate, which we wouldn't be able to do with e to the opposite of x squared, integration by parts wouldn't work. You can try it if you would like. I will show the term by term integral and then write it as a series. So it's an indefinite integral. We will have a constant. Again, with most series, we're going to write the constant in front so that we can write the series after it. The integral of 1 is x. The integral of x squared over 1 factorial, we get x to 1 greater power. And we divide by that power. X to the 4th over 2 factorial. We get x to 1 greater power. and we divide by that power. If we think about the general case, the negative 1 to the n doesn't change. X to the 2n gets raised by 1, so it becomes 2n plus 1. We divide by 2n plus 1, and we also have that n factorial. Integrating that general term is going to help us to rewrite the series, make that a little bit easier. And there is our series. Next, we want to evaluate that on the interval from 0 to 1. And we want to be within 0.0001, I'm sorry, 0.001 of the actual sum. So if we look at the terms of our sequence, or our series, we don't have to worry about the constant now that we have a definite integral. We're going to look at each term It would help if I would have these written correctly. And if we check, because it's an alternating series, we want to find the first term that is less than 0.001. So if we plug in 1, our last term here is 1 over 7 times 6, which is 1 over 42. And if we check 1 divided by 42, we get 0.02, so we need to go at least one more term. The next term would be x to the 9th. Over 9 times 4 factorial. So that would be 1 over 9 times 24. 0.004, we want 0.001. So we can check the next term. And that would be x to the 11th over 11 times 5 factorial. And there we have 0.0007, which is less than 0.001. So we want to include this term and exclude everything after. So our sum will be 1 minus 1 over 3 times 1 factorial plus 1 over 5 times 2 factorial minus 1 over 7 times 3 factorial plus 1 over 9 times 4 factorial. And we can calculate that on our calculator. 0.7475. AP would say, hey, let's round that to 3 decimal places. Or let's truncate it after the 3rd decimal place. At this point, I'm going to stop my recording, and we'll pick this up with a part 2 recording.